In this video, I'll walk through a short EMI measurement summary from recent on-site testing, focusing on the behavior of an insulator installed on a power line. Although an insulator is a passive component and doesn't generate signals on its own, our measurements show that it can significantly influence conducted and radiated electromagnetic noise on the line. I'll start with a quick review of EMI fundamentals, then walk through the measurement results, and finally explain why we see strong interference around 280 kHz after the insulator, even though the dominant noise source appears at much lower frequencies. Let's begin with a few basics. Electromagnetic interference, or EMI, is unwanted electrical noise that can affect the performance of electronic systems. In power systems, EMI typically originate from sources such as switching power supplies, motor drivers, power converters, arcing or partial discharge, external RF sources coupling onto conductors. There are two important concepts to keep in mind: conducted EMI and radiated EMI. Conducted EMI travels along conductors, such as power lines. Radiated EMI propagates through space as electromagnetic waves. In real-world systems, these two mechanisms are often strongly coupled. Any non-sinusoidal signal contains harmonics, which are integer multiples of a fundamental frequency. For example, a signal at 70 kHz will naturally produce harmonic energy at 140 kHz, 210 kHz, 280 kHz. Even if the harmonic amplitudes are lower, system components can amplify or selectively couple them. Now, let's look at the test configuration. We performed spectrum measurements on a power line before and then after the insulator. The spectrum analyzer was configured to observe frequency from tens of kilohertz up to several hundred kilohertz. The goal of this test was not to identify a new noise source, but rather to understand how the insulator affects existing EMI already present on the line. Let's focus first on the measurement before insulator, shown here. Here, we observe strong broadband interference centered around approximately 75 kHz, spanning roughly from 57 kHz to 90 kHz. Key observations: the noise is broadband, not a single discrete tone. The amplitude is relatively high compared to the surrounding spectrums. This suggests an upstream noise source, likely related to switching activity or power electronics. At this point, it is important to emphasize the insulator is not the origin of this noise. Instead, this interference already exists on the line and is being conducted into the measurement location. Now, let's look at the spectrum after the insulator. Here, we see a different dominant feature, a noticeable increase in interference around 280 kHz. At first glance, this might suggest a new noise source. However, when we compare before and then after insulator measurements, a clear pattern emerges. The frequency around 280 kHz corresponds closely to the higher order harmonics of the original 57 to 90 kHz interference band. For example, 70 kHz times 4 equal to 280 kHz. 75 kHz times 4 equal to 300 kHz. This strongly suggests that the energy observed at 280 kHz is not independently generated, but rather derived from the lower frequency noise. So, why does the spectrum change after the insulator? Although the insulator is passive, it can still introduce impedance discontinuities, alter parasitic capacitance and inductance, affect common mode coupling, create conditions favorable for resonance. In simple terms, the insulator can act like a frequency selective structure. This means it can attenuate some frequency ranges, emphasize or re-radiate others, increase coupling efficiency at certain harmonics. As a result, harmonic components that were previously less visible, such as those around 280 kHz, become more prominent after the insulator. To summarize, the insulator is a passive component and does not inherently generate EMI. Strong interference exists before the insulator, primarily in the 57 to 90 kHz range, centered around 75 kHz. The interference observed around 280 kHz after the insulator is most likely harmonic content of the original low-frequency noise. The insulator modifies the coupling and the impedance characteristics of the system, making certain harmonic more observable. This example highlights an important EMI lesson. Passive components can significantly shape the EMI spectrum, even without generating noise themselves. Understanding these coupling effects is critical when diagnosing field EMI issues and then design effective mitigation strategies. Thank you for watching.